This is chapter 4, section 3. We are not learning any new concepts. We're just applying everything we've learned for our whole life and to be able to graph functions. So here are some guidelines for what to look for, what to do. So the first step we're going to see, you're going to look for the domain. Just make sure, if it's a log, it's going to be greater than 0, or if it's a polynomial, it's all real numbers. So it gives you an idea where your graph's going to be located. Now, symmetry, there are two symmetries that's going to help you. Even symmetry. Okay, let me show you what's happening with even symmetry. I'm going to shrink my pen down. So if you have an even function, I'm going to try to explain this to you. So this says you plug in x and you get a y value. Okay, so plug in x, I get a y value. I'll call that x. What is this saying? This is saying what happens when you plug in negative x? Well, negative x is going to be on the opposite side, equal distance away, right? It's going to be over here. That's minus x. So if you plug in x, you get a y value. You plug in minus x, they're both going to get you the same y value. So it's going to be located here. So this is called an even function, and it has y-axis symmetry, because whether you plug in x or minus x, you get the same y value. So it's a reflection over the y-axis. So if the graph looked like this on the right side, if it's even, it's going to look like that on the left side. So that's what even functions look like. Let's take a look at the odd function and see how that works. So the odd function is very similar. So let's look at minus x. I'll keep these same, minus x and x. So they're on opposite sides of the y-axis. So say you look at the minus side and you get a y value. So we get a y value that's right there. Now, what this is saying is the original y value is going to be opposite. So on the x side, you get an opposite y value. So I'm going to be down here. So if I plug in negative x, I get a y value. But on the positive x, you get an opposite y. You're going to be down here. So that's a reflection over the origin. So it reflects over the origin. It's just basically it's a double reflection, x-axis and y-axis. So it reflects it over the x, then over the y, which is origin symmetry. If you draw a line straight through the origin, equal distance on both sides. That distance will be the same. That's origin symmetry. So if a function looks like this on the left side, it's going to look like that on the right side. If a function looks like this on the right side, it's going to look like that on the left side. So these will help you get the general shape of the function if you look at the symmetry. Okay, first and second derivatives, that's what we've been doing for the first few sections. So you're going to look for when the first derivative is 0 or undefined. Those are called critical points. These are the points where a function could change from increasing, decreasing. So you're going to make a table. We're going to do some examples. And with that, you'll also find possible relative extrema at these places. Now, where the second derivative is 0 undefined is analogous to where the first derivative is 0 undefined. Where the first derivative is 0 undefined, it represents places where a function can change from increasing to decreasing, right? But on the second derivative, concave up to concave down. And instead of relative extrema, it was somewhere. Yeah, relative extrema, you could have possible inflection points. So it's a similar process, you're just working with a different derivative. And then the next thing, vertical and horizontal asymptotes and removable discontinuities. So we learned that in chapter 2. And x and y intercepts, you learn that in Algebra 2, possibly Algebra, and again in pre-calculus. So to do this problem, we're just going to do 3 example graphs, but actually I want to do a different thing for you to show you how we put all this together. All right, let's take a look at what all these things say to us, and we will be able to get a general looking graph. So this is easy. I'm going to do that one. At 0, the y value is 2. I like that because I know how to do that. Now, what is this first thing telling us here? If the derivative is positive, we know the function's always increasing. If the second derivative is negative, we know it's concave down. So then we ask ourselves, what does a concave down graph look like? It looks like that. That's concave down. But it also has to be increasing, right? So the increasing part is that. So that's what my graph has to look like. So it gives us the shape of the graph. Has to go through 2. So the graph, and there's not one answer, but this is a possible look of the graph. So that is the answer, a possible graph of the function. All right, make sure you understand these. These are very important. I'm going to go through a bunch of these. Let's do the easy points. 1, -1. I can handle that. Whoa, that's not even close. Maybe I can handle that. 1, -1 is about there. So I've taken care of that. What does this tell me? This says as I move to the right, it approaches 4. That's telling us we have a horizontal asymptote to the right at 4. That takes care of that. Let's see. Let's interpret what this thing is saying. This is saying that the function's increasing where? When x is greater than 1, to the right of 1. And what is this saying? The derivative is -1. So basically it's a line with a slope of -1. So this is a line with a slope equal to -1 for x less than 1, so left of 1. Left of 1. So left of 1, it's a line with a slope of -1. So I can do that. Bam. So to the left of 1, it's a line with a slope of -1. We've taken care of that. To the right of 1, it's increasing to the right of 1. So this is where you have a lot of options. You know it's increasing. I put a line looks like that. It's increasing. It has a horizontal asymptote of 4 as I move to the right. Now, your line could look as long, it could be like wobbling, and it could do that. There are a lot of, oh, actually it's always increasing, so I can't wobble it. I could do this, right? Or you can do this way, then this way. So there's a lot of answers, but the key component, it has to be increasing and approach 4. Let's just keep doing. You're going to get, part of your homework is going to be doing a worksheet like this, and part of it's going to be doing the other things that we're going to be talking about in this lesson. All right. What is this saying? Let me do the easy ones again. Oh, y-intercept of 2. That means it crosses the y-axis at 2. Done. What is this one saying here? It's y equals 1 to the right of 2. Let's just do that. To the right of 2, it always equals 1. That's a constant function. That's what's saying. Y always equals 1 to the right of 2 and equals. Therefore, I put a solid dot, and it's always equal to 1, the y value. Okay, let's look at this one here. This means the function is decreasing. The derivative is negative. Where? Left of 2, where x is less than 2. So left of 2, it's decreasing. And what is this saying? To the left of 2, It's concave up. Well, what does concave up look like? Looks like that. What does decreasing look like? Well, this part's decreasing. So it's going to look like this to the left of 2. So, and I have to go through that point. So I'm just going to draw a curve function like that. So, bam, that fits all my descriptions. That's concave up. And this is decreasing. You remember you're looking from left to right. So that's that graph. Let's just keep going. We have it gets crazier. Okay. F of 0 is -1. Bam, it goes to that point. Taken care of. Now, what does this say? This says it's always concave up. And then this says if the derivative's negative, it's decreasing left of 0. So left of 0, it's concave up and decreasing. Here's concave up. Which part's decreasing? That. It looks like that, left of 0. I can do that. Okay. And then, what does this one say? That says it's increasing to the right of 0. Well, concave up looks like that. Increasing, what does that look like? It's the right-hand side. So it's got to look like that to the right. So that's a possible graph for D. E, wow, F looks ridiculous, but we'll take a look at it. So here, the function is always increasing because the derivative is always positive, okay? And this says, as I move to the right, the function approaches 1. So I have a horizontal asymptote at 1 to the right. So I'll just put a dotted line there. And this says, as I move to the left, I approach -1. So I'm going to have a horizontal asymptote at -1 to the left. And then this says, as I approach 1 from the left, the y value goes really high up. So there's going to be a vertical asymptote at 1. And from the left, it's going to shoot up. That's what's saying. The y value goes up as I approach from the left. As I approach from the right, the y value is going to shoot way down. It's going to go down this way. So I have a vertical asymptote there. Okay. It's always increasing. So I have to draw an increasing function. I have to approach this. It increases, so I move up, and it has to approach that as an asymptote. And here, I'll just draw it and explain. Is this always increasing? Yes, it's getting bigger. Do I approach negative infinity as I get closer to 1 from the right? Yes. And do I approach 1 as x goes to infinity? Yeah. So that's the graph of that one. Now, all of these, make sure they're making sense to you. Make sure they're clicking. Now, this craziness. Let's do one step at a time. F of 3 is 0. Okay, got that. F of 0 is 3. Got that. Is that an F prime of 0? Man, my eyes are bad. That's got to be F of 0. I can't even read this thing. I'm assuming that's F of 0 is 0. Or is that F? No, it's F prime. It's got to be F prime. It's a derivative. Okay. Let's tie all this together. I'm going to make a number line because this is way too much stuff going on here. So I have things going on at 3 is a borderline. So I want to make sure I cover 3. And then 0 is a borderline. 3 is 0 and 3. So 0 and 3 are major points. So what's happening? Let's look at this and we will tie all this together. The derivative is positive to left of 0. That means the function is increasing to left of 0. So I'm going to do increasing here. The derivative is positive. That means the function is increasing to the right of 3. So I know the function is increasing to the right of 3. And we have the derivative is negative between 0 and 3. That means the function is decreasing in that region, right? And then the second derivative is negative. That means concave down left of 3. Concave down, concave down. Whoa, dyslexia. Concave down. And then the last thing, to the right of 3, second derivative is positive. It must be concave up over here. And then at 0, the tangent line has to have a slope of 0. So we know here it's got to be flat, the tangent line. Or in the graph, it's got to be flat. All right. Concave down. Okay, this kind of works out right. Here's concave down. That's increasing. That matches that. That's decreasing. That matches that. So we know it looks like that. In 0, we have the max point, right? So let's do that. And then that's all the way up to 3. And I have to hit 3, 0, so I'm going to hit that. Bam. And then here it's got to be concave up and increasing. It's going to look like that. So my graph is going to look like that. And so that's how you use concavity, limits, and first derivative, increasing, decreasing, to graph graphs. So we got all that. Okay? Now let's go back to what we were doing and see how this all ties together. So that's why we need to find the first and second derivative. We need to check regions of increasing, decreasing, concave up, concave down, inflection points, relative max and mins, and you can see how all that will lead to understanding what the graph looks like. Okay, vertical asymptotes, horizontal asymptotes, removable discontinuities. You should know how to find vertical asymptotes from chapter 2. The definition of them are using limits. I just did one of those in the graph worksheet we just did. But basically they occur when the denominator is 0 in general, but where the numerator does not equal 0. Because if they both equal 0, you'd have actually a removable discontinuity. You could have vertical asymptotes for other reasons, like in logs you have vertical asymptotes. In other functions have vertical asymptotes, but in general, when we're looking for those, if you know the graph of a log, you'll have that. But also, if you have a fraction, when the bottom is 0, you get vertical asymptotes in general. Horizontal, you just take the limit as x goes to infinity or negative infinity. You get the end behavior. And for removable discontinuities, I just mentioned that. They occur when the numerator and denominator equals 0, and those cancel out. And x-intercepts and y-intercepts are helpful for graphing. So you set y equals 0, solve for x to get an x-intercept. And then you set x equals 0, solve for y to get a y-intercept. And again, why do you do that? Because on the x-axis, y is always 0. So if you want to find the x value of a function, it's where y is 0. You set y equals 0, solve for x. Well, x says 3, 2, 1. X is 0 on the y-axis. So if you want to know where a function crosses the y-axis, you just set x equals 0. So simple as that. All right, we have 3 examples. These might get a little ugly, but we're just going to do it. So going through our steps, the domain, this is a polynomial, so it's going to be all real numbers for the domain. All real numbers. So it's going to go forever left and right. No weird things going on here. Number 2, you will notice this is an odd function because if I plug in negative x, what does that look like? That'll be negative x cubed over 3 minus 400 times negative x, which is going to be minus x cubed over 3 plus 400x. But that, if you look at this, that is minus f of x. I'll do this. Because it's just the opposite of the original. So in this case, let me erase this. If you plug in a minus x into the original equation, it turns out that this is opposite of the original. Like, I'll show you why. Let me factor out a negative. You'll get x cubed over 3 minus 400x, which that is that with a negative in front. So that's why it's minus f of x. That's why it's an odd function and has origin symmetry. So I'm going to erase this so I have room to do my rest of my problem. So I'll just say this equals minus f of x. Therefore, it's an odd function. 2. That was 2. 3. So we need to find the derivative. I think we can do that pretty easily. We use the power rule, bring the 3 in front. We get x squared and minus 400. So why do we need that? Because where we've had the critical points, that gives us possible relative max and mins and changing from increasing and decreasing. So we will set that equal to 0. We add 400 to both sides. We square root both sides, and we'll get plus or minus 20, right? So let's not forget the plus or minus. Another way to do that, there's always more than one way to do things in math. We can factor that. That's x minus 20, x plus 20. And you set each equal to 0, you get 20 and negative 20. So we need to make a table and test points around those, because those are the places where a function could possibly change from increasing, decreasing, vice versa. So what do we know? Let's plug in numbers in each region. It's random. You can put whatever number you want in each region. 400 is kind of crazy. I'll put 40. And then you check to see what the derivative will be. If I plug a negative 40 there and there, that'll be negative, that'll be negative. A negative times a negative is positive. I plug in 0, that'll be negative, that'll be positive. A negative times positive is negative. And then I plug in 40, positive, positive gives me positive. So I know it's increasing here, decreasing here, increasing here. The derivative changes from positive to negative. That's going to be a rel max, right? Rel max. And the derivative changes from negative to positive. So this will be a rel min. So a lot of information we just found out from that. Now we have to find the second derivative. We'll do f double prime. And that'll just be 2x. 2x, that's 0. We set that equal to 0, and we get x equals 0. So that's a significant point, and we make a chart again, just like we did for the first derivative. We want to know what's going on around 0 related to the second derivative. And negative 1 and 1, pretty easy. Plug in negative 1, you get negative. Positive 1, you get positive. So we know it's concave down to the left of 0 and concave up to the right of 0. So we're going to just keep moving on. That's 3. Step 4, vertical, horizontal asymptotes. To get vertical or horizontal asymptotes, you take the limit as x goes to infinity of this function, the original, which was x cubed over 3 minus 400x. If you do this, you will find that is infinity. You take the limit as x goes to negative infinity of x cubed over 3 minus 400x. You will get negative infinity. Okay? So I guess to help you guys out on that, you could have factored out an x, and it may have made it easier for you. This is all chapter 2 stuff, so you can refer back to those materials. If I factor an x out, I'm going to get x squared over 3 minus 400. If x goes to infinity, that's infinity. Infinity minus 400 is infinity. So infinity times infinity, that's why we get infinity. That's infinity. You could do the same thing here. You get negative infinity. And that tells you end behavior. As I move to the right, it's going to go up. As I move to the left, it's going to go down. I don't know what's happening in the middle, but that's what those tell me. I'm not going to get any vertical asymptotes because we don't have a denominator that will be 0 here. So we're kind of done with 4. And step 5, x-intercepts and y-intercepts. So if we take our original function, x cubed over 3 minus 400x. If I set x equal to 0, I get y equals 0 over 3 minus 400 times 0. So y equals 0. So when x is 0, y is 0. Now, if I set y equal to 0, I would get 0 equals x cubed over 3 minus 400x. I factor an x out of both. I set each equal to 0. Wow, I hate when that happens because I don't know how to get rid of that. It just kind of disappears on its own. So what I get is x equals 0, x squared over 3 minus 400 equals 0. That's pretty self-explanatory. And then my brain, x squared over 3 equals 400. X equals 400 over 3, x squared. X equals plus or minus square root of 400 over 3. That will be, and if I solve that in a calculator, it's about plus or minus 34, not 43, 34.6. So we're going to tie all this crazy stuff together. How are we going to, okay, this is kind of crazy. Let's look at regions. So we need to look at the 20s and 0. Those are our regions we're concerned about. So to help us in our brain get this kind of situated, what's happening in each region? Okay. To the left of 20, we have increasing and concave down. Increasing, concave down. Between, did I forget a point? No, I'm good. So between negative 20 and 20, we have decreasing, right? I'll just go ahead and write that. It's decreasing here. And to the right of 20, it's increasing, right? So I have increasing here. And we know it's concave down left of 0, so that's concave down. Concave up to the right of 0, so we have concave up, concave up. Whew, we have a lot of stuff going on here. Okay, I need more stuff. I have a relative max at negative 20. So if I plug negative 20 into my function, I get about, and this is huge, 5,333 and 1/3. If I plug in 20 into my function, I get negative 5,333 and 1/3. So I'm going to plot those points. Negative 20, 5,333. Oh my, I got the wrong graph here. Okay, I'm going to have to cheat. I'm going to show you on the final graph because I put the wrong graph there. So that's no bueno. No bueno. I hope I didn't mess up on more than one graph. Okay, so negative 20, 5,330 something. Negative 20, 5,330 something. And positive 20, negative 5,333 and 1/3. So we get those 2 points. Now, doing more points that we know, we found when x is 0, y is 0. So we know it goes through 0, 0. So that's another point. And we found x-intercepts. So we set y equal to 0. And we found the x to be plus or minus 34.6. So if we put dots at those 2 points in the graph, we have that. Now we do this. To the left of 20 is concave down. Concave down looks like that. What does the increasing part look like? It looks like that. So that will be left of 20. But look, here's 20. We do that, and we graph that. Now, I was supposed to be doing that up here, but I put the wrong graph, so it got all confusing, and yeah. Okay, between negative 20 and 0, it's concave down and decreasing. Concave down looks like that. Decreasing is that portion, so it looks like that, and that's how we get that part of the graph. And then between 0 and 20, it's decreasing and concave up. Well, here's concave up. What's decreasing? That's decreasing, so it looks like that from 0 to 20. And from 20 to infinity, it's concave up and increasing looks like that. So the graph looks like that, and we have that beautiful graph. So that's how you use all that information to get that. That's a lot of work. That's a lot of stuff. But it's a great summary of everything we've been learning up to now in our wonderful lives. I'm going to do another one, and this one's crazy. And I'm going to just tell you stuff. I'm not going to, just to save time, I'm going to skip a lot of the algebra, okay? And hopefully that'll make my life and your life easier. And hopefully I got the right graph on this one. Did I? Oh man, I got these graphs all mixed up. I am so sad. I messed up. But we're going to do what we did on the last one for this one. This one's crazy. Okay, take the derivative. So actually the domain, that has a domain of all real numbers, okay? And so it's continuous. It's just a polynomial. Now, a polynomial over polynomial exists everywhere except when the denominator is 0. So we see that the domain is all real numbers except plus or minus 1, because that makes the denominator 0. And we'll talk more about that as we move on. So step number 2, we need the symmetry. And so we're going to put minus x in for x, a negative, and we'll get 10 minus x cubed over minus x squared minus 1. And what will that equal? Wow, that was pretty bad. F of opposite of x will be negative 10x cubed. Now, when we square the negative here, it becomes a positive. So it's x squared minus 1, which is negative 10x cubed over x squared minus 1. Now, if you compare that, what just happened? That should be here. That is that. So when I put in a minus, it comes out the opposite value. Again, that means this is an odd function. So I'm going to erase all this. That odd and even, you might just have to sit with that a while and kind of let your brain contemplate the understanding of odd and even. But this is an odd function, so it has origin symmetry. Oh, and by the way, the previous one had origin symmetry, and we can see that this is just copied on the opposite side, opposite way on the other side, so that matches our origin symmetry. So technically, once we have that side, we know the other is just going to be that. So we could have saved some time on that. Okay, this one also has origin symmetry, so just be aware of that. And that would, like when you're doing a multiple choice test, if you see that, it's easy to pick out which graph matches up better. All right, now we need to find the derivative, and this is where I am just going to fast forward. You don't want to listen to and watch all the algebra, but this is low d high minus high d low all over low squared. Now this simplifies very simply to this. 10x squared, x squared minus 3 over 6, oh, not 6, parentheses, x squared minus 1 squared. Okay? And then if you take the derivative, let's just work with this one. So critical points is where the derivative is 0 or does not exist. Well, this equals 0 when the numerator equals 0. So basically you set each factor equal to 0 and solve. This one you get 0. This one you get plus or minus radical 3. So those are our critical points, but you also need to look at when the denominator is 0. So we are going to set the denominator equal to 0. Well, this is going to be x minus 1, x plus 1 squared equals 0. So you can get 1 and negative 1. So we have a lot of points we're looking at. That's what? Quite a few interesting points that we need to look at there. Okay, now let's move on to our second derivative. That was our first derivative. So again, through the magic of, well, actually we should do our sign chart here, shouldn't we? Let's go ahead and make our sign chart. That will make our life much easier. So we're going to look at the derivative at different points to find the regions of increasing and find the regions of decreasing. So that's our goal here. Okay, so we found 0, plus and minus 1, and radical 3, all of our critical points where magical things can happen. And why do we put the derivative here? Because that tells us increasing, decreasing. That justifies relative max and mins. And that's what this first derivative does for us. I got to plug in a lot of values. Negative 2, negative 1.1, negative 1/2, 1/2, 1.1, and positive 2. Okay, this should go pretty quickly, hopefully. And I'll tell you why. If you look at the derivative, that squared, the bottom's always positive, so we can ignore that as far as positive and negative. And that's always positive, so we can ignore that. So that's not going to make any difference, okay? So all we have to look at is this to determine if the derivative is positive or negative. Okay, plug in negative 2. Negative 2 squared is 4. 4 minus 3 is positive. So it's going to be positive there and positive there. Because it's being squared, it doesn't matter if I put a negative or positive. Make our life easier again. So let's do a half. A half squared is 1/4 minus 3. That's negative. So we know it's going to be negative there and negative there. And 1.1 squared, that's going to be 1.21 minus 3. That's going to be negative. So it's negative there and negative there. And so that's going to be our sign chart. And that's going to tell us where it's increasing, where it's decreasing. That's going to tell us relative max and min. So we'll notice right here, the derivative changes from positive negative. That gives us a real max, an R max there. And here, no, whoa, not that one. Here, the derivative changes from negative to positive. That's going to give us a relative min at that point. I don't see any other relative min or maxes. I think we're good. And real quickly, it's decreasing, 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 increasing, increasing. So a lot of stuff going on there. Now, second derivative, we need to find that. We would actually do our quotient rule there. Low D high minus high D low over low squared. That's going to be a lot of work. A lot more work than I could show you, but the algebra on this is ridiculous, like crazy ridiculous. I don't want to drive you crazy with it. So I'm just going to show you what it comes out to be. If you do all the work, if you want for fun, if you're that adventurous person, you can try. But it comes out to be this. So we want to know when this is 0. We want to know when this is undefined to find possible inflection points and where concavity changes. So to get 0, I do 20x equals 0. X squared plus 3 equals 0. So we get x equals 0 here. This can never be 0. Because if you square something, it's always going to be 0 or positive. If you take 0 or positive, add to 3, you'll never get 0. So that will have no solution. Then you set the denominator equals 0. This factors to x minus 1, x plus 1, and that's all cubed. If you set them each equals 0, you get plus or minus 1. So we're going to make a sign chart for this. We're going to get 0, -1, 1. And now we're looking at the second derivative because we're looking at concavity now and inflection points. So -2, -1/2, 1/2, 2. And we start plugging these into the second derivative. So -2, that will be negative. That's always positive, so we can ignore that. And -2, that's going to be 4 minus 1. That's positive. So we have a negative and a positive giving us a negative. Again, this is always positive, so we're going to ignore that. It doesn't affect anything. But -1/2 times 20, that's negative. And -1/2 squared is 1/4 minus 3, that's negative. Two negatives make a positive. Plug in a half, you put in a half there, that's going to be positive. And a half squared is 1/4 minus 1, that's negative. So positive and negative make negative. And one more, 2, that makes that positive. And this is positive, so we're going to get positive. So what does that tell us? Concave down, concave up, concave down, concave up. Wow, we're not done. We got more to go. Okay, we have more going on in this problem. This is just more tedious, I think, than difficult. We're just doing what we've been doing the whole time. So next, let me see what's on our chart for next. Vertical asymptotes, horizontal asymptotes. So we need to take limits as x goes to infinity and negative infinity and all that good stuff. So where do vertical asymptotes occur? Where do horizontal asymptotes occur? That's what we're looking at. So let me write the original problem down here because I need to scroll down so I can work here. We need to be able to see it. Okay. So vertical asymptotes occur when the denominator is 0. That occurs at plus and minus 1. So the limit as x approaches 1 from the left, if you do that, you'll get negative infinity. So you'd have to plug in values. So on top, if you plug in 1 here, it's going to be positive. But if you're approaching 1 from the left, that's going to be like 0.9999 minus 1 is going to be negative. So positive and negative, that's why you get negative infinity. When the bottom approaches 0 and the top doesn't, you're going to get infinity. You just have to figure out the sign. Same thing. X approaches 1 from the right. As you approach 1 from the right, now you're going to put in like 1.001 there. That's going to be positive. The top's positive, so you can get positive infinity. And this is all stuff we did in chapter 2. It's all review. Now we're going to approach -1 from the left and go through the same process. You're going to get negative infinity, and you're going to approach -1 from the right. And on that, you're going to get infinity. So that's going to tell you what's happening at the asymptotes of -1 and 1. And we'll take a look at that, but that's more stuff to look at. Now, we're going to take the limit as x goes to infinity. of f of x. Woo! That's going to be infinity for this. You would divide everything here by x squared and you would get infinity. And we do the same thing as x goes to negative infinity. If you do that and you divide everything by x squared and go through the same process, you shall get negative infinity for that one. So that's more info. Are we done with all this? No, we're not done. So x and y intercepts. To get the x-intercepts, you set y equal to 0. So you get 0 equals 10x cubed over x squared minus 1. And that equals 0 when the numerator is 0. So that gets you x equals 0. That's the x-intercept. Okay? And for the y-intercept, that's my alarm to get up. For the y-intercept, you set x equal to 0. So if you plug 0 in, you're going to get y equals 10 times 0 over 0 minus 1, which is 0. So let's tie all this together. Our x-intercept and our y-intercept are both 0, so we know it goes to that point. Okay, we have relative max and relative mins. So we have a relative max at radical 3. Now if you plug that into your calculator, your y value comes out to be about 25.9. You're about 26. So negative radical 3 comma 26 would be a relative max. So let me show you. Negative radical 3 is about negative 1.7. Then, whoa, that's huge. At this point, your y value would be negative 26. Negative 26 is about there. That's why we have a relative max right around there. And then we have a relative min where, let me shrink down, a relative min at positive radical 3. And if you plug that in, your y value comes out to be positive 26. So that's why we have a relative min right there. Positive radical 3 and 26 is right around there. So that gets us that point. So we're getting points on our graph. So we've taken care of our relative max, our relative min, and our x and y intercepts. So we have those 3 points on our graph. Now we know as I move to the right, it goes to infinity. So it's going to shoot upwards. As I move to the left, it goes negative infinity. It's going to shoot downwards. So that tells you what happens left and right. Now, one more giant number line with all of our major points. Negative radical 3, negative 1, 0, 1, radical 3. Transferring all of our information, increasing. I could do this on top. Let me do it in blue. Shrink it down so we can see this better. So copying our chart above, we get increasing, decreasing, 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 increasing. And then we get concave down, concave down, concave up, concave, concave up, concave down from 0 to 1. Whoa, back up, Yoshida. Concave down from 0 to 1. Concave up to the right of 1. Concave up, concave up. Now let's check to the left. Concave down to the left of negative 1. Concave down to the left of negative 1. And then between 0 and 1 concave up. Okay, now we have it, and let's connect all these things together. So increasing and concave down. Well, that's concave down. Which part's increasing? This. So it's going to look like that, but it's not. Oh, concave down, sorry. Concave down looks like that. Increasing looks like that. So it's going to look like that to left of negative radical 3. And so that's what's happening here. You don't see it, but it actually is kind of curved that way. Between negative radical 3 and negative 1, it's concave down decreasing. It's going to look like that. So that's the portion we see that there. Oh, the vertical asymptotes. Wow. I don't know if I'm going to be able to do this. It's a vertical asymptote right around here. Can you even see that? I don't think we can even see that. Let me see if I can move that over and make it dashed. I think I can make it dashed. Okay. And copy and paste that. How do I copy and paste? Duplicate. Okay, I think there's another one there, yeah. Okay. So the other thing that's happening, and it's kind of obvious, as you approach negative 1 from the left, it goes to negative infinity, down. As you approach negative 1 from the right, it goes up. And so it fits all of these things. It helps you picture all that. Now, between negative 1 and 0, it's concave up, but decreasing. It looks like that. And that's what we have right there. Let me zoom in a little bit. That's what we have here, is that shape. And then as we go on, between 0 and 1, decreasing, concave down looks like that. Decreasing looks like what? That. So it looks like that, and that's that. Matches. And then decreasing, concave up. Well, here's concave up. Decreasing looks like that, and that matches that. And increasing, concave up looks like that. Increasing looks like that. So everything matches. And we have our relative min, relative max, our inflection point. Oh, I didn't even talk about inflection point. There's an inflection point when the second derivative changes signs. So we have inflection points at negative 1, 0, and 1. There's 0. Actually, I'm a liar, pants on fire. No, we're good. Yeah, concave down, concave up. So there's an inflection point at the vertical asymptote, but the function doesn't exist there, so we don't worry about that. Okay, that's the second example. We have a third example. Craziness here. And hopefully this graph is right. So for this third example, just to save time, I'm going to skip some stuff and get right to the important things. We need the first derivative, and I'm just going to give it to you. The first derivative is going to be this. X minus 1, 9x plus 4 over 3x to the 1/3. So critical points, you set the numerator equals 0, you get 1, and you get negative 4/9. You set the denominator equals 0, you get x equals 0, and so those are your critical points. And by now you know, you check around those critical points to see what's happening with relative maxes, relative mins, increasing, decreasing. And I'm going to pick some points here, negative 1, -0.1, 1/2, and 2. And 2. 1, negative 0.1, 1/2, and 2. 1, negative 0.2, 1/2, and 2. 1, negative 0.3, 1/2, and 2. 1, negative 0.4, 1/2, and 2. 1, negative 0.5, 1/2, and 2. 1, negative 0.6, 1/2, and 2. 1, negative 0.7, 1/2, and 2. 1, negative 0.8, 1/2, and 2. 1, negative 0.9, 1/2, and 2. 1, negative 0.10, 1/2, and 2. 1, negative 0.11, 1/2, and 2. 1, negative 0.12, 1/2, and 2. 1, negative 0.13, 1/2, and 2. 1, negative 0.14, 1/2, and 2. 1, negative 0.15, 1/2, and 2. 1, negative 0.16, 1/2, and 2. 1, negative 0.17, 1/2, and 2. 1, negative 0.18, 1/2, and 2. 1, negative 0.19, 1/2, and 2. 1, negative And again, just to get through this quickly, I'm going to plug that point here, here, and here. You do that in your calculator, you'll see it's negative here, positive here, negative here, positive here. So you know it's decreasing, increasing, decreasing, increasing. And I actually probably should take this derivative for you later and show you how you get that. Because there's some fancy schmancy stuff going on here, so it might be kind of fun for some of you. All right, with this, what happens here? You have a rel max, right? Decreasing, no, rel min, excuse me, because you go from decreasing to increasing. Here you have a rel max because you went from increasing to decreasing, and here a rel min. So we need those points. And I don't think I actually calculated those this time, so we're going to be flying by the seat of our pants this time. Okay, the second derivative, if you went through all the trouble to find that, you would get this. And then you'd find the critical points. Here's what's crazy. This numerator never equals 0. It never does. If you graph it, it's a parabola that's above the x-axis. If you did the quadratic formula, you would have no solutions because it never crosses the x-axis. And like plug in 0 and you get 4, so the vertex is at 0, 4. The denominator, on the other hand, if you set that equals 0, you get x equals 0. So that's your potential inflection point. So we quickly check points around there into the second derivative. Since the top is always positive, you just look at the bottom. And so we're going to get negative there and positive there, concave down, concave up. And we're just going to graph this. We'll go right to the graph. And I wish I made this bigger, but I didn't. But I can copy and paste this stuff. I'm doing this quickly because you guys are probably tired of this lesson. And I'm tired of this lesson because I'm tired. And so we're doing each other a favor. And I think you're getting the hang of this because this is our third example. All right, let's do important points. And let me move this up. So clearly 0, -4/9, and 1 are our regions. So to the left, I'm just going to look. We have decreasing here, concave down, increasing, concave up, decreasing, concave down, sorry, concave up, increasing, concave up. So concave down looks like this. So decreasing is going to be that portion. So that's going to look like that. And increasing concave down is going to look like that. So it's going to look like that. Concave up looks like that. So decreasing is going to look like that, and increasing will look like that. So it's going to look like that on this side. Did I mess up on this side? Concave down. Oh, decreasing. I got increasing. Oh, no. Why is my brain not processing right? Let's do this over again. So decreasing, concave down. Here's concave down. Do I have the right thing going on? I don't know why my brain... Oh, no wonder I'm so sloppy here. Look, that's a fourth power. You take a negative fourth power, it's positive. So that is positive. Now my brain concave up in both those regions. So it's going to look like that. Okay, let's do this. Decreasing concave up, that. I have a relative minimum. If I actually calculated that, I would get -4/9, and I'd get a y value. You'd actually find that y value. And your relative max, you would get 0, 0. So you'd actually plot that point. And if you found the y value for 1, you would find that point. You would have found your two relative mins and your relative max. So those points would be found for you. And then decreasing concave up, it looks like that. So we get that portion. Increasing concave up, that's increasing, that's concave up. You get that portion. Decreasing concave up, you get that portion. So we get that. Increasing concave up is that portion, you get that. So that's how you get that graph. That's how it would look. And so what I want to do is something that's kind of cool. We're going to take the derivative and show you how from this derivative you can get this, because some of you would it'd be a nightmare finding that. So this is a bonus edition, extra feature. It's kind of a cool skill to have. So how do you find f prime of x? What we're first going to do is rewrite this. We don't want a product rule. That's foolishness. We're going to distribute this, and we're going to get 9/8 x to the 8/3. Okay, that's 6/3 plus 2/3 is 8/3. That's how that comes about. Then we're going to get minus x to the 5/3 minus 2x to the 2/3. And then for the derivative, we're just going to use our power rule. So it's 9/8 times 8/3 x. Subtract 1 from that, you can get 5/3. Minus 5/3, you bring the 5/3 in front, decrease that, you get 2/3. Bring the 2/3 in front and decrease that power by 1, you get -1/3. So here's our derivative. These 8's are going to cancel. You get 9/3 x to the 5/3 minus 5/3 x to the 2/3 and -4/3 x to the -1/3. What do we do next? We're going to factor out a 1/3 and an x. See, they all have the 1/3. And we take the lowest power of x out, -1/3. So what's left? I get 9. And then I'm going to get x to a power. Okay? So that power plus that power must be 5/3. Well, if you're taking away 1/3 to get 5/3, that has to be 6/3. Minus, I took away the 3, I'm left with the 5. X to some power, but whatever's there, that plus -1/3 must be 2/3. So it must be 3/3 minus 1/3. And I took the 3 out, I took that out, left with a 4. And so that 3's on the bottom. That negative puts, let me try this, that negative puts it on the bottom. And we have on top 9x squared minus 5x minus 4. That's how you get the derivative that I found, and you can factor that. So that's your bonus edition, and that's the end of this video.